Hello, welcome to CE 241 Material Science. So today we will talk about various properties related to strength. So what is strength? Basically, it's a measure of stress that the material can withstand. There are mainly two types of strength that we talk about in civil engineering: yield strength and ultimate strength. We discussed these terms last week. Yield strength is the stress at which a material begins to plastically deform. Ultimate strength is the maximum stress the material can withstand during a tensile test. These values may change considerably with respect to the way the material is deformed. For example, mode of stress, type of stress, rate of stress application, they all impact the strength values. On right, you see four graphs. The first one is a ductile metal. You don't see a yield point, but you can use 0.2% offset method to get its yield point. And on the second plot, you see a obvious yield point. And on the bottom, you see a brittle solid and an elastomer. Strength is impacted by the loading rate. Here you see an example, a smaller loading rate and a larger loading rate. A smaller loading rate will yield a lower yield and a lower ultimate tensile strength, whereas a larger loading rate results in a, which means larger loading rate means a quicker loading, and a smaller loading rate means a slower loading. A faster loading results in a higher yield and higher ultimate. Also decreases percent elongation. Why? An increased rate gives less time for dislocations to move past obstacles. Therefore, strength data are usually obtained from lab tests, which are performed under strictly standardized specimens under controlled conditions from stress-strain relationships. We also went through brittle failure and ductile failure last week, so let's revise. Ductile materials, they undergo large amounts of plastic deformation before they break. These materials fracture at very large strains, for example, gold or mild steel. Brittle materials, whereas, they fracture at very low strains with little to no plastic deformation. For brittle materials, the concept of yield strength is irrelevant as they don't deform plastically. Glass and ceramics or porcelains, they are examples. Actually, there is no definition of how a ductile material and a brittle material is separated. Typically, a material which has a strain at fracture less than 5% is considered brittle. And actually, let's revise when it is considered ductile. On top, you see an example of a brittle failure, relatively brittle failure, and a relatively more ductile failure. The blue one is more brittle, and the red one is more ductile. So when you look at a fracture surface, you can actually understand what kind of a fracture it is. Here you see three examples. Necking down of specimen near fracture. The highly ductile fracture in which specimen necks down to a point on the top example. On the second one, you see a moderately ductile fracture after some necking. This is called cup and cone, actually. And the last one is a brittle fracture without any plastic deformation. So it is as if it is cut with a knife, so it's a square break, a clean break. Also, the brittle surface looks more shiny if you look at it. And a ductile failure in metals, especially ductile failure, looks less shiny. So let's revise what happens in a moderately ductile fracture. So everything starts with necking. Then we see some void nucleation. Voids will grow and they will link. And then you will see some shearing at the surface and finally our fracture. So here you see some SEM images for a moderately ductile fracture. You see the voids and you see the cup on cone shape of the fracture surface. So how do we gauge if our material is ductile or brittle? A ductile material is the one which deforms appreciably before it breaks, whereas a brittle material is the one which does not. Ductility can be defined as strain at fracture. It is commonly expressed as percent elongation or percent reduction in cross-sectional area. For metals, if a percent reduction in cross-sectional area is larger than 50%, we consider this material as a ductile metal. Percent reduction in area and percent elongation are often comparable. Why? Because crystal slip does not change material volume. But sometimes percent reduction in area can be larger than percent reduction in elongation if internal voids form in the neck. So actually ductility can also be dependent on temperature. Many types of steel are ductile at room temperature, but they can become brittle when temperature drops below the ductile to brittle transition temperature. This temperature is actually an important design consideration because ductile failure is normally preferred to brittle failure, especially in civil engineering applications, because brittle failure is very sudden, which can be catastrophic. An example to this can be brittle failure of Titanic. Icy waters of North Atlantic are thought to have caused the steel of the ship's hull to drop below its ductile to brittle transition temperature, resulting in a catastrophic brittle fracture under impact loading. So last week we actually solved this example, but let's revise. We have a cylindrical specimen of steel. It has an original diameter of 12.8 millimeter and it's tensile tested to fracture. We found to have an engineering fracture strength of 460 megapascal and its cross-sectional diameter at fracture is 10.7. Let's determine the ductility in terms of percent reduction in area and true stress at fracture. So we calculated percent reduction in area, basically the area initial minus area final divided by area initial. So it can be calculated as 30%, which is less than 50%. So our metal is considered not ductile. And we can also calculate the true stress at fracture. We know our instantaneous cross-sectional diameter. So the first thing we need is the load that we apply on our material. We know our engineering stress, which is 460 megapascal, and we know our initial area because we know our initial diameter as 12.8. So we multiply 460 megapascal with our initial area, which is 128.7 millimeters square, and this will give us 59.2 kilonewton as our load. And now we can calculate our true stress, which is basically force divided by instantaneous area. So 59.2 kilonewton divided by our final area, which is 89.9 millimeters square, gave us 658.5 megapascal. Also, last week we talked about stress-strain curves of polymers. Here you see stress-strain curves for a polymer at different temperature. Temperature which is much higher than glass transition temperature, a temperature that is close to glass transition temperature, a temperature 0.8 times glass transition temperature, and a temperature that is much lower than glass transition temperature. Glass transition temperature of a material characterizes the range of temperatures over which this glass transition occurs. It is always lower than the melting temperature of the crystalline state of a material, if one exists actually. Some materials don't melt, as you know. So polymers actually differ dramatically from metals. What happens is, let's look at the stress-strain graph at glass transition temperature. It actually looks very different than what we have seen in steels. It differs because neck does not continue shrinking until the specimen fails. Rather, it stretches only at natural draw ratio, which is a function of temperature and specimen processing, beyond which the material in the neck stops stretching and new material at the shoulders actually stretches down. The neck then propagates until it spans the full gauge length of the specimen. This is a process called drawing. Not all polymers are able to sustain this drawing process. So what happens is, the thing is, initiation of a neck is harder than pulling a neck for these materials. So what happens is, the neck forms, but it cannot go basically to a smaller diameter. Instead, it basically, the neck elongates as polymers stretch further. So instead of a neck, we see something basically with a rather uniform diameter at this elongated part, as you see on the image on top. So now I want to introduce a new concept, toughness. It is the energy absorption capacity after fracture. It is basically the energy needed to completely fracture the material. In a static strength test, the area under the stress strain curve gives the amount of work done to fracture the specimen. Basically, this is known as modulus of toughness. This is the amount of energy that can be absorbed by the unit volume of a material without fracturing it. So the unit under the stress strain curve is Pascal. So it actually can be written as Newton meter divided by meter cube, which is basically Newton meter joule divided by meter cube. So don't forget, the area that you calculate will be in joule per meter cube, which means amount of energy per unit volume. So to calculate the total energy that is absorbed, you need to multiply this value with the volume of your object. So modulus of toughness is basically, this can be calculated by integrating from 0 to your final strain, integrating your stress. So if the area under the stress strain curve is large, the material will have a high toughness, so it will be able to absorb larger amounts of energy before fracturing. For a material to have high toughness, it should have a good balance of both ductility and strength. So let's go through energy absorption values of various materials. Ancient iron is relatively pure iron. Modern spring steels, spring steels are basically a wide range of steels used in manufacture of springs, prominently in automotive and industrial suspension applications. These steels are generally low alloy manganese, medium carbon steel, or high carbon steel with very high yield strength. This allows objects made of spring steel to return to original shape despite significant deflection or twisting. And then we have yew wood. Yew wood is actually basically a type of wood, and you might know it from Harry Potter. So Lord Voldemort and Ginevra Weasley, they had wands from yew wood. And tendon in our muscles, or rubber. So what we see, a wide range of models of tightnesses. Ancient iron has 0.01 megajoule per meter cube, whereas rubber has 10 megajoule per meter cube as models of toughness. So maximum energy that can be absorbed per unit weight can also be interesting. What you can see, per unit weight, rubber can absorb the most energy, whereas the ancient iron absorbs the least energy. Also, you see a plot here from high carbon steel, medium carbon steel to low carbon steel. High carbon steel is the strongest. It reaches the highest ultimate strength. Low carbon steel is the most ductile. It reaches the highest percent elongation. Medium carbon steel is the toughest because it has the largest area under stress strain curve, so it absorbs the highest amount of energy. So let's solve a simple question. Consider the engineering stress strain curves given below. Determine what the area under a stress strain curve represents and give its unit. So basically, the area under a stress strain curve represents modulus of toughness or energy absorbed, and its unit is Pascal or joule per meter cube. Based on the stress strain curves, state which material has the highest tensile toughness. Here you see is the green one has the largest area under the stress strain curve, so it can absorb the highest amount of energy per unit volume. So it is the one with highest toughness. So based on the stress strain curve, state which material has highest tensile ductility. Ductility is related with percent elongation or percent reduction in area. So we see our unreinforced polymer, the red curve, has highest strain. So that would be the highest ductility. And the last question is, can you explain why ceramics have lower toughness than metals? Ceramic materials are made of covalent bonds. These are rigid directional bonds. And ceramics do not deform plastically because of their nature. So what happens is we do not see this plastic deformation portion. We only see the elastic, mostly elastic portion of our stress strain curves. So the area under is much lower. Energy absorbed is not. I also want to talk about impact test or notch toughness. It is ability of a material to withstand an impact blow. We actually use two tests, Charpy test and Izod test. They are very similar. Basically, the energy absorbed is the difference in height between initial and final position of the hammer in the Charpy test. The material fractures at the notch and the structure of the cracked surface will help indicate whether it was a brittle or ductile fracture. The difference between Charpy test and an Izod test is the shape and placement of the specimen. And Izod test is usually used for polymers. It is basically very similar configuration. On right, you see the example of a Charpy test. You actually place our notched specimen, you release the hammer, and basically it fractures our sample. And in Izod tests, the specimen is placed perpendicular actually instead of a horizontal placement, and shapes a little bit. So impact performance also depends on atomic arrangements. FCC alloys generally show ductile fracture mode. HCP alloys show generally brittle fracture mode. And BCC alloys show brittle modes at relatively low temperatures and ductile mode at relatively high temperature. Below you see an example. The green one is FCC metals, for example, copper and nickel. So you see a relatively the temperature dependence is relatively low. But you check BCC metals or polymers, actually you see a high temperature dependence. Actually, there's a specific temperature, ductile to brittle transition temperature, where you see a very low performance, and above that temperature, you see a much higher performance. So BCC alloys are very, their impact performance is very temperature dependent. I also want to talk about resilience. Resilience is energy absorption capacity during deformation. So it is actually the amount of energy the material can absorb without suffering permanent damage. So we can find it by integrating from 0 to yield strain or stress. And this area can actually be approximated by 1/2 yield strength times yield strain. So this is actually equal to the square of yield strength divided by 2 times elastic modulus. So here is an example. Determine the modulus of resilience for a titanium alloy with elastic modulus of 113.8 gigapascal and yield strength of 880 megapascal. So let's use the triangle approximation. So it is square of the yield strength divided by 2 times elastic modulus, and it will give us 3.4 megapascal. And this is actually 3.4 joule per meter cube. So if you want to get the energy, you need to multiply this with the volume of your object. Let's solve a simple question on temperature dependence. Below you see engineering stress strain behavior for pure iron at 3 different temperatures. The green one is 25 Celsius, the blue one is minus 100, and the red one is minus 200. So which one has the highest resilience? So you check up to yield, and the red one has highest area. So red one shows highest resilience. Which one has highest toughness? So we check area under, and the blue one has the largest area under. So it is at the minus 100 Celsius. pure iron. Which one has the highest yield point? Actually, the red one, as you can see, it barely starts yielding. Which one has highest tensile strength? Again, the red one. Which one has highest ductility? The green one reaches highest strain, so it has highest percent elongation and percent reduction in area. Which one has highest stiffness? Actually, their elastic moduluses are the same, so their stiffness are relatively the same. Another question. So I will give you a couple minutes to think. If you can pause this question and try to solve it yourself, and then watch the solution, that will be very useful for you. So assume a cylindrical specimen of aluminum with a diameter of 12.8 millimeter. And let's think that you use a gauge length of 50.8 millimeter and you pull it in tension. And please use the load elongation characteristics tabulated below to complete the parts of the question from A to F. So first thing, please plot the data as engineering stress versus engineering strain. Compute the modulus of elasticity. Determine yield strength at strain offset of 0.2%. Determine the tensile strength of this alloy. What is the approximate ductility in percent elongation? And complete the modulus of resilience. So please pause the video and try to do it yourself. First thing is first, let's plot it. So we have our load. We can calculate our change in length. So we can convert this to strain and stress. So we can basically plot our stress strain graph. And I also zoomed in to the first part, so it will be easier for us to calculate the resilience. So ultimate is 370 megapascal. You can see it from the graph. And the yield, you can calculate it by 0.2% offset method, is 285 megapascal. And elastic modulus is basically slope of this initial portion, and we calculate it as 59 gigapascal. And resilience, we approximate it with the triangle formulation. So it's yield strength square divided by 2 times elastic modulus. So it's roughly speaking 0.65 gigapascal. Of course, this is this particular one is an approximation. And also, let's calculate the percent elongation. And the percent elongation is 0.165. Percent elongation is actually strain. So let's solve a question. The stress strain tests were carried out on 5 different metals, A, B, C, D, and E. The results are shown on the figure below. Select the metal for respective properties. So which one has highest resistance to plastic strain? Which one has highest toughness, lowest stiffness, highest ductility, highest brittleness, highest resistance to elastic deformation, and highest tensile strength? So please pause your video and try to solve it. And then continue. Okay. So the highest resistance to plastic strain is E because it has a highest yield point. And highest toughness is actually D because it has the highest area under. Lowest stiffness is actually B because it has the lowest slope. Highest ductility is C because it has highest percent elongation. Highest brittleness, basically the one with least amount of strain, is E. Highest resistance to elastic deformation is again E because it has highest yield. And highest tensile strength is D because it reaches to the highest ultimate. Let's start with a new concept. Hardness. It is a material's resistance to localized plastic deformation. It is a quick and practical way of estimating the quality of a material. Large hardness means resistance to plastic deformation or cracking in compression. and better wear properties. Early hardness tests were based on natural minerals with a scale constructed solely on the ability of one material to scratch another that was softer. A qualitative, somewhat arbitrary hardness indexing scheme was devised, termed as Mohs scale, which ranged from 1 on the soft end for talc to 10 on the hard end for diamond. An unknown material will scratch a softer one and will be scratched by a harder one. Here you see talc with scale 1. Gypsum, you can actually scratch it with a fingernail if you want, because fingernails hardness is 2.5. We have calcite with scale 3. Gold is around 2.5, 3. Copper is 3.5. So copper can actually scratch gold. Fluorite around 4, iron around 4, 5. Apatite around 5. Knives and glasses, they're around 6 to 7. Steel nails around also 6 to 7. Quartz is around 7. And masonry drill bits around 8.5. Corundum, which is a common material on phone screens, is around 9. And diamond is at 10 points to diamond. Yeah. Hardness of a metal is determined by pressing an indenter on surface of the material and measuring the size of the indentation. The bigger the indentation, the softer the material. So most plastics are relatively soft, then comes brushes and aluminum alloys, then easy to machine steels, then file hard, then cutting tools, nitrided steels, and finally diamond. There are different tests. We can use Brinell hardness test, Rockwell hardness test, Vickers hardness test, or Knoop hardness test. But general procedure is pressing the indenter onto a surface, then we withdraw the indenter and measure the hardness by measuring the depth or width of the indentation. Here is a summary of our most popular hardness tests. We have Brinell, Vickers, Knoop, and Rockwell. So they all have different types of indenters, either spherical or conical or a pyramid shape. And we apply different loads. And there is a formula to calculate the hardness number, which is then used to calculate several mechanical properties related to that material. Let's go over popular hardness tests. The first one will be Brinell hardness. So you start with a diameter D indenter and you press the load P for 30 seconds and you measure the indentation diameter. And from the following formula given on the screen, you can calculate Brinell hardness number. A soft brass will have a Brinell hardness number of 60. A mild steel will have a Brinell hardness of 30. Anneal chisel steel, 235. White cast iron, 415. And nitride surface will have 750. So let's solve a simple example. So we have a 10 millimeter diameter Brinell hardness indenter, and it produced an indentation of 1.62 millimeter indentation in a steel alloy. The load was 500 kilogram force. Can you calculate the Brinell hardness number? And what will be the diameter of the indentation to yield a hardness of 450 Brinell hardness number when a 500 kilogram force load was used? Please pause your videos before solving the question. You can check the formula on the previous slide if you want. Let's solve it together. So the first question is very straightforward. We know the formula to calculate Brinell hardness number. 2 times load divided by pi times diameter of the indenter times diameter of the indenter minus square root square of diameter of the indenter minus square of the diameter of the indentation. So you calculate your Brinell hardness number as 241. The second part of the question is calculating the indentation to yield a Brinell hardness number of 450. So we just basically shuffle the formula a little bit and calculate the indentation diameter as 1.19 millimeter. So I want to go back to previous slide one more time. So 215 is similar to annual chisel steel at 235, and 450 is more similar to white cast iron at 415. So just to gauge the hardnesses of these materials. The second hardness test I want to discuss is Rockwell hardness. It is the most common one. Actually, you can see the equipment on the right, top right. So this time, instead of measuring the indentation diameter, you measure the indentation depth. Of course, the surface roughness may affect the results. So what you do is there is an initial penetration with load P1 and then a final load P2. So you measure the second depth and then you take the difference. So the minor load to eliminate the surface problems is around 10 kilogram, and the major load has three categories, A, B, and C. It can be 60 kilos, 100 kilos, or 150 kilos. So it becomes Rockwell A, B, or C. And on the A, you use a diamond. On B, you use a 1/16 inch ball. On C, you use again diamond. So the last one I want to discuss today is Vickers hardness test. Instead of a sphere, a diamond pyramid indenter is used and the indentation is averaged. You put the average into a formula and you calculate your Vickers hardness number. So just to compare these tests a little bit, binaural hardness test is the first widely used standardized hardness test. It determines the indentation hardness of metal materials, and it is typically used for materials with a coarse surface or a surface too rough to be tested through other methods. Binaural test actually is not useful for fully hardened steel or other hard materials. However, it often leaves a large impression on the metal. Binaural test is also very slow, actually. And the Rockwell hardness test is very popular. It is developed to provide a less destructive alternative to Brinell test. This differential depth method eliminates the errors associated with mechanical imperfections because you first indent with a minor load and then you do indent with a larger load. So this eliminates a lot of problems. It is quicker and cheaper than Brinell and Vickers tests. The Rockwell test requires no material preparation and hardness value is easily readable without any extra equipment, making this one of the most commonly used methods for measuring metals hardness. And the last one we discussed was Vickers hardness test. Making use of this diamond indenter, the Vickers hardness test is done with less force and more accuracy than Brinell test. By magnifying the surface of a metal, this test can target specific microstructural constituents too if it is necessary. You can also assess the quality of heat treating or surface hardening operations. Requiring an optical system and for sure material prep, the Vickers test incurs higher costs, takes longer to complete than Rockwell test. So there is also a knob test, but I'm not going to discuss it today. So basically, hardness tests are performed more frequently than any other mechanical tests for several reasons. They are simple, inexpensive, ordinarily no special specimen need to be prepared, and the testing apparatus is relatively inexpensive. Test itself is non-destructive. The specimen is neither fractured nor excessively deformed. A small indentation is the only deformation. Other mechanical properties often be estimated from hardness, such as tensile strength. Comparison of several hardness scales is given here. We have knob hardness, we have Brinell hardness, Rockwell B, Rockwell C, and we have also Mohs hardness here in that particular plot. Thank you very much for listening to me today. I will also discuss creep and fatigue on my next video, and hope to see you in person when the pandemic ends. Bye.